My name's Lindsay Beavers, and I come from Scotland. My university's Heriot-Watt University, but I used to teach here. So used to teach here last year. I left in 2010, August 2010, and when I was here I used to teach the hydraulics component of the environmental flow allocation summer course. So today we're going to talk about hydraulics within environmental flow allocations. You've had hydrology from Susan. You've had the kind of ethos and the overall concept from J. O'Keefe and implementation. Now we're going to go into a couple more with this lecture and the next lecture of detailed considerations. So what are we actually going to look at within environmental flows? How do we predict things? How do we look at making sure that we get the correct habitat conditions? And if we break that down, we can look at hydraulics, we can look at geomorphology, which is sediment, we can look at water quality, and we can look at different ecological considerations. But this lecture, we're just going to look at the hydraulics. So get my clicker to work. So in the overview of this lecture, we'll try and stop in 45 minutes and have a break. But we're going to look at why do we need hydraulics, different types of flow, what kind of different types of flow bring different things, bring different habitats. So we'll look at those. We'll look at the theory, for engineers that might be something that will be something that you've dealt with before, the theory behind hydraulic calculations. But we'll look a bit at that and how we get to where we are, and then how we implement the theory for prediction purposes. How do we use that in models, for example? Look at a couple of case studies, and then we will summarise for today, for this morning. So why do we need hydraulics? We need it because it's what links us between hydrology to all of these components that we need for environmental flows. Hydraulics links the hydrology, where we get the flows, meters cubed per second, but it links it to water quality needs, fish biologist needs, vegetation, and geomorphologists. This is what we'll do this afternoon. But for example, water quality specialists need to know how much water there is, how much capacity will there be for spills to disperse, what are the different flow components, what are the different velocity components. Fish biologists may need a critical depth for spawning, a particular velocity for movement of fish up and down the river. Vegetation specialists may need to know about different inundation regimes. So maybe twice every year a particular area may need to be inundated. And that's what hydraulics gives us. So it gives us this link. It allows us to link flows, which we can maybe get predicted meters cubed per second, depending on where you are in the catchment, or you might get a particular amount of flow over a day, which is a release from a dam. And you can take that, and then with the use of hydraulics, it can give us the components. So it can give us depth, D, velocity, V, wetted perimeter, P, which is the amount of cross-section that is wet, and the width, W, so the water width. So it allows us to link flow to the requirements of other specialists. So if you like, hydraulics specialists are those people who link the flow to the specialist. So we interpret what the flow might mean for different specialist requirements. So we can take the discharge, and if we see here, this is a cross-section, two-stage cross-section. So there's your river down here. The floodplains, these are very engineered obviously, but what it does is it takes the discharge and it links it to water level or depth from the bottom, so a particular depth at a particular place, the flow width, how wide that flow is across the channel, Velocity, how fast, the speed of the water in particular places. For example, in the centre of the channel, the velocity will be faster, depending on where the flow is moving fastest. That depends on many factors, and you can predict that using hydraulic theory. And the wetted perimeter, which is the outside, how much of the cross section is actually wet. But what I just showed you there is an engineered cross section. This is very, very simple. This is nice and easy to conceptualize and to understand. But actually, hydraulic channels in reality, when we go out and look at the river, they're never that simple. They're always complex, and they're part of a natural system. So what we need to be able to do is to break these down to understand how the flows move through the system. And we do that through a way of simplifying. And we do that by simplifying the physics of what goes on at a cross-section, and then approximating this system from the data and from the physics. So then we can understand what is going on at a particular cross-section. And from that simplification, we can scale up or scale down in detail and in space. I hope that becomes clearer as we go on through the lecture. But we'll have a look first at some flows. What do we actually mean by complex natural channels? Let's spot some different types of flows. Let's look at different types of flows and what they mean to different habitats first. So, different types of habitats need different types of flows. And ecology sits on top of these flows, and ecology requires different things from the river at different times. So if a river was uniform and like a canal that you see out here, you would only get some forms of habitat, some forms of species. So diversity is often what we look at to support really diverse ecological communities. So if we're talking about diversity, here, for example, are two examples of low flow. Here you can see that this river is running really low, only small amounts of water in it, and actually ephemeral or intermittent rivers. A lot of ecology requires that you have intermittent rivers. These are not necessarily bad. So recognizing that that is a function, or that is something that happens in the river or stream that you're looking at, is important when you're looking at environmental flows. If it's supposed to go dry every year, then putting flow in the river permanently will change the ecology. We also have very different flows. Here we can see, for more perennial rivers, very uniform flow, smooth flow, rippled flow, and we could expect to see one form of ecology in this river. Perhaps you would have particular fish species. Depends where you are in the world, what you would find in your river. But then as the flows move faster, as they get more, they have more energy, you start to see broken flows, turbulent, broken wave and chaotic flows. And with those you get a different type of ecology, those that can cope with the turbulent flows. You also may find that you will find pools and riffles where you get this areas of smooth flow followed by much faster running flow like this. And then you have areas where you may find refuge. So this diversity is what you want to look for. So across a cross section you may not see only one type. So here we have rippled flow, but some very smooth flow over here. Here in this stream here you can see that we have small chute flow, so we have small steps and pools. So we have areas where you will have refuge for fish and for macroinvertebrates, and then areas where there's faster running water which oxygenates that water. Here again you can see areas of faster running flow, and then areas where it's more smooth and deep. But what is important is recognising the components of the ecology that require the water. What do you want in ecological terms, and what does that need? What does that mean for the hydraulics? Do you want riparian forest, which requires you to inundate it every year? So do you need to get the water onto the floodplain every year? Or are you looking for to make sure that particular fish are safe, and in which case you need to talk to the fish biologist about what kind of conditions that particular species particularly needs. And then you need to go out and recognise that on the river. But to do that, we really need to think about how we break up the catchment, how we break up what we're looking at. When we're looking for environmental flows, we tend to be looking downstream of large dams. And downstream of large dams, we need to be able to break this information up. We need to be able to know at which reach we're looking at. Because perhaps not the whole area downstream of the dam is of interest to us. Perhaps there's only particular areas. Or maybe it is over the whole area. So this consideration of scales is very important. And when we talk about scales, we're not just talking about spatial scale, so in terms of size. We're also thinking about temporal scale, so how fast something is, or how long, over what period of time we want to think about something. Do we want to be able to predict flows for 10 minutes? That might be the length of a particular flood in the headwaters of a particular river. Or are we talking, let's say for the Zambezi, about months when we're talking about a flood situation? Or in the Mekong, we're talking about several months when we're looking at that. So do we need to think about those flows over a year? Do we need to think about them over several months? Or are we talking about them over a much shorter period of time? Are they quicker? Are they more flashy? In the UK, for example, we tend to be thinking about flows only over a few days because our rivers are much shorter. Perhaps if you're on Jamaica or San Martin, that's the kind of time that you'll be thinking about, because you're looking at much shorter rivers. But when your rivers are much longer, you've got much more consideration about the length of time over which a flood appears. So also, do we need to know the velocity at every point across that channel? Let's have a look at this river. We could say that you could average that flow perhaps across that cross-section, and that wouldn't be too much of an assumption. But if we look at this one, perhaps you want to know a lot more about the flows across in different points in that cross-section. And this one, you might want to know exactly where the velocity is fastest and where it's slowest, because that might have more information about a particular species. So it depends on your river, and it depends on where you are in the catchment, but it also depends on what you want to predict, what kind of ecology the ecologists are asking you to ensure is safe. So we also need to consider the spatial scale. So do we need to consider the river over the whole basin, over the whole catchment? Do we need to consider water balance, which you'll have come across as water resource managers, certainly. Are we considering about thinking about how much water arrives at a particular place? Or are we actually just going to focus in on a particular reach, where we want to look at more detail about the particular flows that are there? Not how much, but what happens to that flow? What is the velocity at particular points along the reach and across the reach? And to do that, we break the flow into cross sections. So here, just to give you an example, here we can look at a basin scale. So are we looking at the whole of that catchment? And perhaps that's the job more of a hydrologist, to look at what comes in from the whole catchment and what happens to the flow as it comes out into a reach. When we're talking about a reach scale, perhaps we're only talking about a section of a river. could be hundreds of kilometres long, but we are talking about a stretch of river, a particular length of river. And you can break that up into smaller sections which may have more representation the smaller you get. So you may find more representative reaches where the flow changes, where you have different features of the flow. And then you take it right down to the local scale where we look at cross sections. And it's those cross sections that allow us in hydraulics to be able to predict velocities. And that's how we break it down for the theory. So cross sections become very, very important. If you look here, this is a river, so it's flowing down, there's a tributary joining and a confluence. And across here is these red lines, they're cross sections. If we want to break this up and break down this river into cross sections, we can then apply hydraulic theory to it, and that's how we build models. So a cross section would be, if you look at this blue line, it's basically cross section through the channel, and we need to measure those. And this is an example of, some of you may know Marluce. This is some of the work Marluce did on her PhD, taking cross sections in a particular river in Tanzania. But how we do that is we set up a good datum on one side, we set up a transect, a cross section, so a point across the cross section, and then at every point across that cross section we use this meter rule to work out what the depth is from the datum. So we can work out what a cross section is through that river. But we can't just consider the river channel, we also have to consider the floodplains as well, particularly if we're talking about inundation extent. We want to know how often the water goes onto the floodplain, we want to know how often or how deep it gets on the floodplain, how deep it gets in the channel. And depending on your river, that may be more or less important. In a river like this, you don't really have floodplains. It's very, as you already identified, it's isolated in its own canyon. But a river like this could easily inundate, has much more pronounced or obvious floodplains. So when we're taking cross sections, which is an important component because this is how you link your hydrology to your information for your biologists in environmental flows, you take cross sections. So an important part of the environmental flow allocations is taking cross sections. And here we can see an example of a river. It's a meandering river, so it's a river in its lowland phase, or in the middle reaches phase before it comes down to the estuary. And here we would measure the main channel for the cross section, but we would need to pick up the whole river corridor width, which would be the width from here to here, which includes these meanders. So it's a considerably larger area. So when you're setting out this cross section, you would start your datum, forget that it does that. You start your cross section here, but you would continue all the way across to the other side of the corridor. So that you pick up that information, this storage available to that river, the floodplain. How about this one? Where would you say is your main channel? Feel free to shout out.
From reef to reef from the borders.
You want to, there you go, use the red and point out where you think it is.
From this point until this point.
That's the main channel.
That is the main channel. Because here the river is eroding or have erosion this part.
It's active, it's definitely active, yeah.
Even this upper part.
How about the river corridor then?
The river corridor?
Yeah.
So it's the place in which the breathing part of the river is moving.
So what you pointed out I would call the river corridor, and then the channel is just the active bit, the bit that you see with the water. Yeah. So, thank you. Here we go with the main channel width, so the active, where you actually see water flowing, and then as you identified, this corridor width, which is where the water would be contained during a reasonable flood, significant flood. Now we're going to look at the key physical principles. When we look at a cross-section, we can estimate, or we can approximate how we change the flow into water levels and depths and velocities by approximating physics. And the theory that we use to do that is that, first of all, mass is conserved, which is quite a simple one to think about, and also that we use Newton's second law, where force is equal to the rate of change of momentum. So we use those two key physical principles. And we always do that between two cross-sections, which is why these cross-sections are very important. Simply, we always look at this a certain amount of channel between two cross-sections. If we say mass is conserved, that's very simple. If more mass goes in, then the water level goes up. If less mass goes in, the water level goes down. So mass being conserved is actually quite a simple process to think about. When we think about Newton's second law, because we have to use both of these two components because we have two unknowns, things are a little bit more difficult. And what we have to look at is all of the different forces on this section of water between two cross-sections. So we look at the force of gravity working to move it downstream, the resistance from the bed and banks acting to move or to stop that water moving downstream. That can come from material, vegetation, it can be quite complex, or in a canal, for example, it might be much more simple, it's just concrete sides. So depending on your river, depends on the more complex resistance that you get from the bed and banks. You might also get constriction of flow, narrowing of the channel. So maybe there's a bridge, maybe there's a constriction. That also acts against gravity. And then you also have to balance up the pressure due to the depth of water at these two cross sections. So when we bring together all of those components, and we can approximate them and use Newton's second law to bring together what is known as the Saint-Venant equations. Have any of you heard of the Saint-Venant equations? Mm-hmm. Yeah? Yeah. So we've got a good covering. So the Saint-Venant equations are the basis for one-dimensional modelling for hydraulic flow. They are basically partial differential equations in terms of x, distance along the channel, and in terms of t. These are one-dimensional here, you can also make them two-dimensional. And in two dimensions you're taking in components of velocity in x and y. And here, in one dimension, we use the component of q. This top equation is the conservation of mass equation, and this one here is what we got from the Newton's second law. So this is for completeness. We don't need to know too much detail about this, but it's this theory that we can use to predict water level and velocity at particular places, because we can get velocity from q over a in one dimensions. So that gives us our velocity. And because they're partial differential equations, we use a numerical model. Because a numerical model uses numerical approximations to calculate the water surface slope at any particular point in a channel. So water surface slope, water surface, so depth, and velocity at any cross-section in a channel. But we can simplify that. That's when we're looking at it in a complex way. We can simplify this So if we assume that the flow doesn't change, we're looking at a steady state flow, only one flow per time for a particular amount of time, we can say it's steady. And then we can reduce the previous equations to the backwater equation, which, given a downstream depth and knowing the bed slope, we can then calculate depths along that slope. So you may remember from your hydraulics the backwater equation. So that allows us then to plot a water surface profile. So that's a simplification. So depending on how complex we want to get, we can go from complex, we can simplify it, and actually we can simplify it even further. If the channel shape doesn't change, if we consider that it's uniform, this is ideal world, perhaps in a canal again. If the channel shape doesn't change, and if we've also said here the flow doesn't change, so the channel shape is uniform, the flow is steady, we can then say that bed friction is balanced by the gravity slope. So S0 equals SF, so the gravity slope, bed friction and the gravity slope. So we can say that one balances the other. And if we can do that, then all we really need to know about is the friction. How can we quantify friction within a cross section, and then we can use equations such as Manning's and Chézy, which we will come on to in a minute. So how do we measure that friction? Well, we can measure. We're now sitting in a privileged piece of time where there's been a significant amount of research that's done that has approximated friction. There are many different ways. There's Manning's, there's Chézy, there's Colebrook-White equation, which uses a different factor. Then there's also something called KS, which is different roughness depths. And these come from experimental and full-scale measurements. And the analysis of those have produced empirical formula. And we can look at a cross-section and we can start to estimate what the friction is. So here we can see that we've got very fine sediment, so we've probably got a lower friction, smoother bed than here, where you can see we've got cobbles and pebbles. We've got bigger sediment, more vegetation, complex vegetation, so we have higher friction. It slows the water down more. And we can use, you'll probably have come across these equations, Manning's and Chézy. I, being from the UK, tend to use Manning's equation. Here in Europe, they tend to use Chézy much more commonly. And that's just two different ways of measuring friction. So you have Chézy coefficient, and here you have Manning's N. And that, it just means it's a different factor, which helps you understand roughness. So how do we get N and C? Again, we're in a good position. There are lookup tables. If you've ever heard of HEC-RAS, which is a one-dimensional modelling program that's freely available, they have a very good lookup table. So they give you a good idea of what different Manning's Ns you might encounter given different particular rivers, different rivers. There's also photos which match photos to Manning's N, but there's also perhaps the most famous book which most of us all go back to, which is Van de Chau, Open Channel Hydraulics, 1954 I think. And this book here has some of the best ways of referring what your Manning's N or your Chézy number should be given your particular river stretch or reach. So you'd be looking at different Manning's N's numbers. For example, in the channel I would be looking at possibly from 0.045 to about 0.025. 0.025 when I have a much smoother slope. We also have the ability to use more sophisticated tools. So we just went from the complex hydraulics, so from we looked at the Saint-Venant equations, and then we simplified it down to measuring or looking at just Manning's equation. If we go back to the Saint-Venant equations, we can employ models. We can have Saint-Venant equations in one dimension. We can have the Saint-Venant equations, as I mentioned, in the 2 dimensions. So we've got x and y coordinates. We can also include the z direction. So we can have flow in 3 dimensions. So in more complex projects where we have funding or time available, we can use more sophisticated models to link our flows to our velocity. And this comes back to the question, do you need to know the water level across a cross-section? Do you need to know the velocity every 5 centimetres? Or can you know it just one velocity across the whole cross-section? And that allows you to think about what kind of tool you might want to use if you have the money and the available time to predict that in different dimensions. And some of you may have come across them that there's different courses that are run at the moment for Delft 3D and Mike 21. Delft 3D, developed here in the Netherlands in Delft Hydraulics, is a pseudo 3D, 3-dimensional package which does give you water levels and velocities in 3 dimensions. Mike 21, developed by Danish Hydraulics, DHI, and that one gives you flows in 2 dimensions, very commonly used tools. It doesn't have to be that complicated, but it can be, and it can be really useful. So here's an example here. This is from Professor Wright, who used to work here. He worked on the River Idle project. Now, you can see that the flow is moving this way through the channel. So what we're looking at here is a channel. The colours indicate how fast the river's going, so these are the vectors. So you can see that we've got an area of very high, fast flow. So this is the baseline, pre-scheme. So you can see that we've got low flow, moving to fast flow as it goes down the river. And what they wanted to do with this example is that they wanted to create more habitat where you had areas such as this, low flow, to encourage particular fish species to be able to breed. Okay? So what they did was they built, so you can see this is a zoom in here, and this is the post scheme where they've built a buffer which directs the flow to the other side of the river. So you've got this period of high flow being directed to the other side of the river, and then you've got an area of refuge on the other side. So what they've used the model to do is to predict that they're improving the habitat by their intervention. So here we can say habitat of the adult chub. An adult chub is a particular fish species. So here we can see the habitat index pre-scheme, and here we've improved the habitat here and given them an area of refuge. So you can use the models to show exactly what you want, or exactly what the fish biologists tell you is needed from a habitat perspective. So it can be quite a powerful tool, but only if you link it to what you understand from the ecologist that is needed from the habitat. Does that make sense? We have I have another short case study that I wanted to show you here. And this one is in Scotland, where I worked on a particular in Scotland we call small rivers burns. It's just a particular thing we do in Scotland. So a small river is a burn. And this river here, very small river, had to be realigned as part of a project. But it was known to have particularly diverse macroinvertebrate, particularly diverse geomorphology, so sediment. So it was considered quite a nice, important river that was a tributary to a much larger river, which was very important for salmon, and also for mollusk called the freshwater pearl mussel. So to ensure that there wasn't any change to this river geomorphologically, because we didn't want to release sediment downstream, because that really affects mollusks because they breathe through their shell. So any extra sediment could kill these mollusks. We wanted to make sure that when we realigned this river, it was done in a very sensitive way. So this is a way here, instead of linking it directly to fish habitat, we had to link our hydraulics to understanding of sediment. So we had an extensive baseline assessment. We looked at the hydrology, we looked at the hydraulics, water quality, geomorphology and ecology. So we had the different experts in. And so what we went out to do was we also did sediment sampling, and we'll do that, we'll have a look at that this afternoon. Channel capacity checks and channel stability checks. So when we went to look at the design, we could use this sediment sampling from what we knew was existing, and we could use that in our new design. We also used something called the CES software. So where this is a particular situation where the river's smaller, so we don't need to use a three-dimensional model or a two-dimensional model. Here, what we've done is simplified it down to look only at cross-sections. And here we're applying Manning's equation at the cross-sectional space scale. So the fluvial audit, what we call a geomorphological assessment in the UK, indicated that it was morphologically diverse, dominated by fine gravel and coarse sand transport, which means that that does move when the flow is strong enough. Coarser bed particles appear to be stable, they're not actually moving, so the cobbles are pretty stable in the river. There is some localised incision, so perhaps this river is partially degrading, but only a little. And there's a lot of wooded debris and leaf litter, which does improve the diversity where it is, and also provides nutrients into the channel. So that's the existing. So we took that existing information, and then what we did was design a two-stage channel. So here you can see short floodplain, small uniform channel, but we've got this floodplain here, which allows the water to go out of bank. So we simplified the hydraulics, and we predicted water levels and velocities, which we then linked using the Hulstrom curve. So we've used simple hydraulics to link to the Hulstrom curve, which indicates when we have sedimentation, when we have transport, and when we have erosion. So we wanted a stable channel, a channel that didn't erode because we didn't want the sediment moving downstream. So we could design the channel alignment, design the gradient of that channel to make sure that it's a stable channel, but it still allows, it's still using as much of the natural environment as it can. So here, the purpose of this case study really is to look at the fact that we can again link these hydraulics to other indicators, and those other indicators are what's important. And as a hydraulic engineer, you have to talk to the other specialists to get the information from what they want, what they need to either happen or not happen. If it's velocities, happen in terms of spawning. If it's sediment, here in terms of velocities, so the sediment doesn't move. So the design ended up with a cascade, a two-stage channel here, and then a cascade because we had to drop the gradient, which we then had to design the bed morphology so that the bed sediment could be stable. We designed the overall gradient, and we made sure that the sinuosity, and we'll do that this afternoon, looking at the amount that the river channel wiggles, if you like, was replaced. And then we designed this cascade where we needed to get the particular channel under the road. But we could use the simplified hydraulics to do that design. So, that brings me to the end of the hydraulics lecture today. So in summary, what we've had a look at is why do we need hydraulics in the first place? And the fact is we need them because it is the link between the flow rate and detailed requirements. We've really looked at different types of flow in the environment. We've tried to get our brains working because we're specialists in so many different subjects, and that's what we need to do. We need to identify the hydraulics that are important to different components for environmental flows. Then we've looked at the theory, how, as a hydraulic engineer, as a hydraulician, you can link the information that you need from all the specialists to the flows that are required in the environment. And we've looked at how you would measure the cross sections that you would need to apply that theory, because you would need to collect those cross sections to put into a model, be it a very simple one like we looked at with the CES, with the Kinkosi berm because it was so small, or the two-dimensional model when we're going up in complexity. And then we looked at a couple of case studies where we have taken either habitat requirements or morphological sediment requirements and linked that directly to the hydraulics and predicted an outcome that we needed for a particular river.